Hi, in this video we are going to talk about the theoretical background for binary search trees, so let's get started. Okay, we have been considering arrays and linked lists, and we come to the conclusion that whenever we would like to insert a new item into an array, it is quite slow because we have to rearrange the whole array. So that's why it's going to have ordo and linear time complexity. If we would like to insert a new item into a linked list, on the other hand, we are going to end up with a quite fast algorithm. You just have to update the references and it can be done in ordo 1, so constant time complexity. But searching is quite fast with binary search if the array is sorted. For an array, it can have logarithmic time complexity. Searching is sequential for linked lists, so that's why we do not prefer searching in a linked list. Removing an item is quite slow for sorted arrays because we have to reconstruct the whole array again with linear time complexity. Removing an item is quite fast for linked lists because we just have to update the references, so we can do it in ordo 1 constant time complexity. So what's the conclusion? That basically sometimes it's very good to use arrays, sometimes it's good to use linked lists. We have to know in advance that what's going to operations are going to be performed by the user to be able to decide what data structure to use. But it's kind of a nonsense situation. Sometimes the user wants to search something. Some users are going to search more. Some users are going to inserting new items more frequently and so on. So we are not able to decide at compile time that what data structure to use. Because as you can see from this table that the running times are quite different. So if we use linked lists, we can do it in ordo 1 constant time complexity, but if we use arrays, we are going to end up with linear time complexity, so it does matter. And basically that's why binary search trees are very good, because binary search trees are going to make all of these operations quite fast in logarithmic time complexity. And what's very important, that this binary search tree is going to be predictable. We know that, okay, logarithmic complexity for all the operations. It doesn't matter whether the user is going to search more, it's going to insert at the beginning of the list or the end of the list. The operation is going to take ordo, logarithmic and time complexity. And okay, you may pose the question that why is it so important? It is so important to be able to construct the data structure at compile time that's going to work fine for every operation. Let's consider Facebook. There are several users who's just going to search for other users. For example, they are curious about the photos of their friends, but there are other people on Facebook who likes posting photos, posting quotes and so on. So one user likes something and the other user is going to use the software in a different manner. So that's why it's very important to use data structures that's going to have predictable running times. So what is a tree? We have nodes with the data and connections between the nodes. Basically these are the edges. So a tree, it's quite intuitive, consists of nodes and edges. The root node, basically in this case, is the node A. We have a reference to this, so all other nodes can be accessed via the root node. In the tree, there must be only a single path from the root node to any other nodes in the tree. If there are several ways to get to a given node, then if it's not going to be a tree. For example, this situation, it's not going to be a tree because we can get from A to D directly, or we can go from A to C and then from C to D. So there are two ways to the same node, so it's not going to be a tree. Okay, a node directly connected to another node is going to be called a child. The opposite relationship is the parent node. So the children of A are the node B, node C, node D. The child of B is the node E. The parent of E is the B. The parent of B, C, and D is the node A. So basically child and parent relationships are not independent from each other. Okay, So what about binary search trees? We have been discussing trees in the main, but what about binary search trees? Every node can have at most 2 children, a left child and a right child. The left child is smaller than the parent and the right child is greater than the parent. These are the most important features for a binary search tree. For example, let's consider this tree on the left. The root node is the 12. The right subtree consists of a single node, the 20. It is greater than the parent 12. And all the nodes in the left subtree are smaller than the parent 12. The 4, the 1, and the 5 are all smaller than their parents, the 12. So basically, it is a valid binary search tree. You may pose the question, okay, why is it good? We have been talking about arrays, linked lists. They are going to solve our problem. Why to bother about binary search trees? Because in every decision, we get rid of half of the data in which we are searching, and that's why the type complexity is going to be very, very favorable for binary search trees. It is very, very similar to binary search. We can get rid of the data on every iteration, and that's why the time complexity will be ortho-logarithmic, so ortho-log n. Okay, what about the height of the tree? Basically, the height of the tree is the number of layers it contains. The layer 1 is going to contain a single node, so it has 2 to the power of 0 nodes. The layer 2 contains 2 nodes, so 2 to the power of 1 nodes. The layer age, basically the age is the height of the tree, how many layers do we have, is going to contain 2 to the power of age minus 1 nodes. In general, this age is going to be proportional to the ortho-logarithm n, so the logarithm of the n. If this is true, then the tree is said to be balanced. If this is not true, then the tree is unbalanced, which means that it is asymmetric, which is a problem. Why is it problematic? Because the running times are going to be reduced, so the logarithmic time complexity is not going to be met if the tree becomes unbalanced. So the height of the tree is the number of layers it has. The length of, basically, the formal definition is that the length of the path from the root to the deepest node in the tree. And we should keep the height of the tree at a minimum, which is approximately age is equal to the logarithm n. Why? Because if the tree is unbalanced, then the age equal log n relation is no more valid and the operation's running time is no more logarithmic. So that's why we can end up with a quite slow algorithm, even with binary search trees, if the tree becomes unbalanced. And unfortunately, for most of the cases, this is what's happening. So that's why we are going to consider balanced binary search trees, such as AVL trees and red-black trees. So this is an unbalanced tree. On the left, we have the root node, it has a left child, and the left child has another left child, so it is not balanced. The number of left children is not equal to the number of right children. The tree-like structure on the right is going to be balanced because the number of right subtrees and left subtrees are going to be approximately equal. Why is it good? Because for balanced trees, the operation's running time will be favorable, will be logarithmic. For unbalanced tree, we can end up with ortho and linear time complexity, and basically we have been talking about linear time complexities with linked lists, so we don't want to end up with a data structure that has the same running time as the linked list. So, just to summarize again, binary search trees are data structures, so we are able to store data in a binary search tree. And it keeps the keys in sorted order so that lookup and other operations can use the principle of binary search. Each comparison allows the operations to skip over half of the tree so that each lookup or insertion or deletion takes time proportional to the logarithm of the number of items stored in the tree. So this is the ortho logarithm n running time complexity. And this is basically much better than the linear time, so the ordo n required to find items by key in an unsorted array, but slower than the corresponding operations on hash tables. It's very important to see the evolution of data structures, that we started arrays, linked lists. We come to the conclusion that okay, we are able to do better. We are able to construct binary search trees with the logarithmic time complexity, and we are going to discuss hash maps, dictionaries, and ternary search trees, and we can come to the conclusion that we can even do better, and we are able to achieve approximately ordo 1 constant time complexity for these kinds of operations. Thanks for watching.